Hi, today I'm going to be deriving the kinetic theory equation, which is PV equals a third NM C bar squared. Firstly, I'm going to make 5 initial assumptions for our model of molecules of gas in a box. Number 1, the molecules are point molecules. Number 2, they do not attract one another. Number 3, they move in continual random motion. Number 4, their collisions are elastic. And number 5, collision time is short. Now we can begin. Now, first you can start by imagining you have a box. I'm going to draw one here, and it is going to look terrible. Oh, that's not the best. You know what? I think that's better. We're just going to imagine that this has dimensions Lx, Ly, and Lz. And there's a particle in that box with a velocity in each direction. So this particle has a velocity in each direction, and those velocities respectively are v, s, and t, which means that its overall speed will be given using the Pythagorean theorem. C, which is its overall speed, would be given by root v squared plus s squared plus t squared, because v, s, and t are its components, are the components of its velocity in each direction. Now, when the particle collides with one of the faces of the box, its momentum would reverse direction. So first, let's let the particle collide with the left side face. Its momentum would reverse in that direction during the collision from mv to minus mv, because remember the collision is elastic. So it would go from nv to m minus v. Therefore, the change of momentum, or m delta v, would be equal to 2mv, because it would go from mv to minus mv. Now, the time between successive impacts is given by because if you think about it, the particle is moving between the faces. It's travelling at a certain speed, it's travelling a certain distance, therefore the time between it reaching each face would just be given by a simple speed equals distance over time equation. Subbing our values in, we would find that t equals 2lx over v. Right? Here it's 2 because it has to travel to one side and then back, so we double the distance. Our distance is Lx because that's the dimension, and we use our velocity as v because that's our component of velocity in the x direction. So if this is a face, this is a face, and this is a particle, for it to travel there and back again, it travels a distance of 2Lx, and as it's travelling at a velocity v, the time taken between these successive collisions is given by 2Lx over v by a simple speed equals distance over time equation. Using Newton's second law, me just rewrite that. T equals 2Lx divided by V. Using Newton's second law, F equals ma, also known as m delta V divided by T. We find that the force of the impact would be given by F equals, and remember we found that our change in momentum was equal to 2mv because it reversed. So that would be 2mv divided by T, which is given by that. So then we'd write in 2Lx divided by V. Now, this would cancel because this is dividing, but it's also on the bottom. It means we times, and we would end up with mv squared divided by Lx. And that would be the force. We know that pressure equals force divided by area. And the area of the face is the multiple of the other two dimensions. So if it's traveling along the x-axis and it collides with this face, then the area of this face will just be the product of this dimension and this dimension. So we can find that P is then equal to mv squared over Lx divided by area, which, let's move that up. P equals F over A, which is therefore mv squared divided by Lx divided by the area, which would be a multiple of the other two dimensions, which would be Ly multiplied by Lz. Now, simplifying this, we would find that equal to mv squared divided by Lx times Ly times Lz. Now, a neat property of this is now that the product of all three dimensions is by definition the volume. So it means that P equals mv squared divided by big V for the volume of the box. Now, for a box with n molecules, large N will be the number of molecules here. The total pressure will be the sum of pressures due to each molecule. So P total, which I'm just going to write as big P, will be given by P1 plus P2 plus P3 all the way up to P n, the nth molecule. It would therefore stand to reason that, let me make a bunch of space, P is equal to mv1 squared over V plus mv2 squared over V, and so on up to mvn squared over V. Factoring out m over V, we would find that P equals m over V, big V, for volume, V1 squared plus V2 squared plus V3 squared, and so on up to Vn squared. The sum of this, if divided by n, so all of these divided by n, would give the square of the average velocity. We can therefore then write that P equals nm over V multiplied by V bar squared. So obviously for n particles, if we divided that by n, it would be V bar squared. So just multiplying it by n gives us a much easier way to write this. So we say that P equals nm over V multiplied by V bar squared. This, however, only takes into account the velocity in one direction. But the particles have 3 degrees of freedom. They can travel in 3 different directions, x, y, or z, and they have 3 components of velocity, v, s, and t. Taking that into account, we would therefore end up with an equation that looks more like v bar squared plus s bar squared plus t bar squared for the components of velocity in all 3 equations. But here are 3 degrees of freedom, and we have to correct for that. So what we do is we divide by 3. As shown earlier, this is all equal to c squared, which would then give us nm over 3v multiplied by c bar squared, or written in the form as above, PV equals a third nmc bar squared, like shown right here. And that is the kinetic theory equation.